Welcome back, friends, for another lecture on quantum field theory and quantum entanglement. We have been looking at quantization of the Dirac fields, and now what we did was that we just assumed that you can do the quantization exactly like what we did for the Klein-Gordon field. Okay, now we had the misgivings whether we can do it directly or not, because first of all, spin half particles we know from quantum mechanics are fermions. So when you, and quantum field theory is essentially a theory of multi-particle states. So and in okay, and in while we quantizing the Klein-Gordon field, we created this n particle states, right? Essentially one particle state, two particle states, n particle states, and so on. So if you are creating such n particle states, how are you making sure that these particles uh, satisfy the corresponding statistics, essentially, because multi-particle states, if you remember correctly, that if you exchange two of the fermions essentially in the multi-particle states, essentially they should pick up a minus sign. So this thing should be encoded, but for the present we neglected it essentially. This is what also Peskin calls how not to quantize a Dirac field, essentially, if you look at Peskin's quantum field theory book. Okay. So, but anyway, let us just go ahead and try to expand it in terms of what we tried to do was impose this commutation relations exactly like what we did for the Klein-Gordon field, essentially, except taking into consideration the spinorial indices. And then we expanded this into these modes, essentially positive energy and negative energy spinors. These are ladder operators, exactly like what we did for a charged scalar field, except the difference between the charge scalar field and here is that we have spinors here for the representing the spin half nature of these particles, essentially. So US of P, Vs of P, which are positive energy spinors and negative energy spinors. Putting back into this, and then we impose all other commutators to be vanishing, and we see that what we see is that this BB bar and the C, one of these thing has a negative sign in front of it, otherwise these commutation relations will not be satisfied. These commutation, this you can check it explicitly, that is what we will do today. And now this would mean that if there is a negative sign here, that means that you are creating particles with a negative norm, essentially there. As you will see, there will be positive energy particles, but they have negative norm essentially. So the norm should not be negative, so as you know in quantum mechanics. So let us go ahead. So let us see why this happens essentially. So let us compute this explicitly, psi bar, the commutation relations which we imposed for the quantization, essentially psi dagger of y, okay, this is sum over r s integral d cube p d cube q 2 pi by 6 1 by root of 4 EP EQ. Now you see here you get BP commutator R BQ dagger S commutator UR of P US of Q dagger e power I xp minus yq. Okay. So this is just substituting these relations, so winning the mode relation, expansion relations into the commutator of this one essentially, and the second term will be CPR dagger CSQ as this commutator, which is This is a commutator on B dagger and the other one is C dagger C. V R P V S Q dagger e power minus I x p minus y q. Okay. So when you compute now let's substitute BQ, okay, using these relations, meaning let's impose delta RS, delta P minus Q. For C, let's impose this is positive essentially, okay. And this is minus delta RS P minus Q. So let's impose this minus delta RS here, and this will give me P gamma 0 to the bar e power I P x minus y so plus V of S P V bar of S P gamma 0 e power minus I P bar x minus y. So it okay, when you do all this, okay, then you show, okay, then you use the outer products relations. So you can use the outer product relations, which are essentially UU bar P slash plus M, and then we also have VB bar minus P slash minus M. So we did them, put it back into this, okay, put this outer product relations into this, and finally you show that, and finally there is a trick. You have to change P to minus P integration, essentially P to minus P integration has to be done. And finally what you get is psi of x, psi dagger of y is equal to dqp 2 pi cube so e power I p x minus y. So this is nothing but your delta function of x minus y. Okay. So these relations are consistent. Okay. Now these relations are consistent with each other, imposing the quantization conditions with negative norm, essentially with this on this harmonic oscillator thing, on the Labrador operators, is equivalent to using commutation relations, or commutation relations demand at least one commutation relation of the commutation relations on the field operator, sorry, to summarize or equal time commutation relations on the field operator. On the field operators demand at least one of the commutation relations on the ladder operators to be negative. Okay, this is the main thing. So, if we quantize it by imposing equal time commutation relations, you will end up on ladder, the commutation relation on the ladder operators to be negative essentially. Now, how will you go about done? How will you go about um, okay to impose essentially now how will you go about quantizing the Dirac field? How to go about? Now, the point is that is it really a problem essentially? Now, you can ask now you can ask that these commutation now if there is negative problem, now you say that if I interchange A dagger to A, will it solve the problem? Okay, suppose if I define that A dagger annihilates the vacuum, but A is the one which is like a creating operator, but then it will it solve the problem? So, you can have all these questions essentially. So, we can think of interchanging A dagger to A, we can think of interchanging A dagger to Uh, so, all this will not solve the problem essentially. At the end of the day, what you have is essentially that these states uh, uh, have a negative norm. Now, if you impose, on the other hand, say you interchange C to C dagger interpretation, change the interpretation. So, that means say that C is a creation, C is a creation operator and C dagger is the annihilation operator. And then, so you do not worry about the negative norm states and everything, we can make a consistent we can. So, you change the Hamiltonian in that manner, Dirac Hamiltonian. Okay, we will try to explore the Dirac Hamiltonian, which is given by this essentially. The Dirac Hamiltonian is nothing but H psi bar okay. So, we want to have conserved energy, no, at the end of the day we need to have positive energy, conserved energy. Now, what will turn out is this using this Hamiltonian, the Hamiltonian has with B states as it creates a positive energy state okay, and with a negative energy So, C dagger also creates positive energy states. So, there is no problem essentially as of now, but these states will have negative half. Okay, this is the point I am trying to say essentially, that if you create these things, you can create positive energy states, but these states have negative now. Okay, but then the problem comes, the Hamiltonian, okay, P as minus EP bar Cp of S. Okay, this is the problem essentially, that the Hamiltonian with the when it the commutation of the Hamiltonian with the annihilation operator Cp, okay, which has the negative Hamiltonian negative what do you call, negative commutation relations, the Hamiltonian is not bounded from below. So, if the Hamiltonian is not bounded from below, so it means that you keep creating these particles and then it keeps tumbling into lower and lower energies. So, you can never have any probable meaning continuously you will be continuously producing these negative energy these particles, and the Hamiltonian will keep crashing down essentially. It does not, you cannot make an interpretation of the vacuum, you cannot create a particle with okay, uh, leading to misleading interpretations. And wrong interpretations. Okay, so all these problems have come to us because we treated, okay, so whatever way we try to solve this problem, it's always going to end up into meaning some problem or the other, in the sense that it's always end up the vacuum will be completely gone and the negative the energy is not bounded from below. That means that you can go to negative infinity and you can end up having nonsensical results and so on. So, and the problem came purely because you are treating fermionic particles, which are spin half particles, exactly in the same way as a bosonic particle. So, or the root cause of all these problems is that we are treating spin half particles as bosons, meaning obeying Bose-Einstein statistics, whereas they should obey Fermi-Dirac statistics. Okay, the root cause of this is that we are treating spin half particles as bosons, okay, but they should not be. They should obey. They obey actually. They obey, whereas they obey. So things which obey Fermi-Dirac statistics, we are trying to treat them as some things which obey Bose-Einstein statistics. That's the problem. Essentially, you are treating fermions as bosons, whereas they are actually meaning which should not be happening essentially. So the relation between spin and statistics is given beautifully in terms of the spin statistics theorem. So we are just not going to prove it, we are not going to deal with it, but we will just say what it says is that all integer spin particles satisfy Bose-Einstein statistics and all half integer spin particles satisfy Fermi-Dirac particle statistics. Okay. So, this is the spin statistics theorem. So, given this, instead of using commutators, if something obeys, if particles obey to have states obey Fermi-Dirac statistics, one should use anti-commutator for quantization. Instead of commutators. So, that is the main thing essentially, that we should use anti-commutators, okay, because we need to, these are spinor fields, right, essentially they okay, they obey Fermi-Dirac statistics because they have spin half, they interpret for spin half particles. So, they use, one should use anti-commutator relations for quantization rather than commutation relations essentially. Okay. So, this is the main point, for if you want particles which are satisfying Fermi-Dirac statistics, you need anti-commutation relations essentially. So, with this we start with the commutation relations. Now, take the field operators psi and pi is nothing but psi dagger, okay. But now impose anti-commutation relations between them instead of commutation relations. So, this leads to, you have, so the new relations are psi alpha of x, psi beta of y is equal to psi dagger alpha of x, psi beta dagger of y, anti-commutator relation, and the other one is psi alpha of x, psi beta dagger of y, delta alpha beta delta cube x minus y. Okay. This is the crucial thing. This is the crucial thing. Now, the thing is that what is curly brackets? Curly brackets between two operators is equal to AB plus BA. Okay. Whereas the commutator between two operators, as you know very well, is AB minus BA, but instead of that, the anti-commutator with has a plus sign essentially. So, we impose the conditions on the anti-commutation relations essentially, the anti-commutation relations for quantization. Now the mode expansion of psi and psi dagger, the same thing, are the same. Okay, you keep the same mode expansion, but what happens is, so if you want the mode expansion, okay, so this is essentially you have psi is equal to integral d cube of p 2 pi cube 1 by root 2 e p. So I am just checking whether I am using the same notation as previously, us of p bar e power plus ip of x plus c p dagger as v of s p dagger e power minus p of x. Okay, this is the same mode expansion, but this mode expansion will lead to anti-commutation relations, because now we are imposing anti-commutation relations on the field operators. So this will lead to anti-commutation relations also on the B and C operators. So this would mean, but okay, the same relations will lead to anti-commutation relations on this B, P, R, B, Q, S 2 pi cube delta RS delta cube P minus Q Cp bar R Cq S 2 pi cube delta RS delta cube P minus Q, and rest of the things will just vanish. Okay. Okay. So the rest of the commutators, anti-commutators will just vanish. So you'll have, okay, uh, so you'll have things like, you know, B, B, C, C, B bar, B bar, or B dagger, B dagger, C dagger, C dagger, all of them should vanish essentially, all the commutators should vanish. Now calculate the Hamiltonian exactly like what we did for the last time. So in fact in the beginning of this class we calculated the Hamiltonian is given by here, put it back, so minus I gamma I del I plus m. So now put it back into this, and the Hamiltonian is S, you see the Hamiltonian now has a negative sign between B dagger B P and CP dagger essentially. Now this you can re-express it. So this will become d cube P 2 pi cube EP. Now using the thing, you end up having BP S dagger BPS. So you have the the annihilation operator on the right. So CP dagger S CPS minus 2 pi cube del cube 0. Now when you do the normal ordering, this term goes to 0. This term goes to 0 after normal ordering. It is obvious, right, essentially like what we had earlier. Okay. So, now you see the Hamiltonian is not bounded from 0 below, you have normal ordering, Hamiltonian is well behaved. Let me put it in, what I mean by well behaved is it's not unbounded from below, okay, it is well behaved. And so you have a proper nice Hamiltonian, you can build positive states with the positive meaning all the negative and positive energy states, and now you can also have, you do not have states with a negative norm, no states with negative norm. So, everything works very well. So, this is how one quantizes the Dirac equation, the Dirac field. Essentially you quantize it by imposing anti-commutation relations instead of the commutation relations. Okay. So, we spend a lot of time trying to quantize the Dirac field with commutation relations, and we see that we ended up with problems. But now instead of that we imposed anti-commutation relations and everything works out very well, and you have the same field mode expansion, and it gives a well behaved Hamiltonian and well behaved states essentially. So, this is the reason why the Dirac quantization is a very important thing, because it is a lesson in spin and statistics. Now, you cannot treat the bosonic fields in this, you cannot quantize the bosonic fields in the same manner as you quantize the fermionic fields, or the vice versa, meaning you cannot quantize the fermionic fields which are essentially like spin half particles. The example is a Dirac equation, Dirac field. You cannot quantize it exactly the same manner you quantize bosonic fields, because they obey completely different statistics, and this will play a role when you are quantizing n particle states essentially. Okay. Very good. So, let me stop here, and we will continue with the Dirac equation, Dirac field quantization. In the next lecture we will start building propagators, and then we will move to interaction theories and everything. So, let me stop here, and let us meet again for another lecture on quantum field theory. Thank you very much.